Okay, so now we're going to change gears a little bit and move into chapter 12. We're done with infinite series, and the rest of the quarter really is going to be focused on moving towards studying calculus in 3 dimensions. We call it multivariable calculus. Everything we've done up till now, well, most everything has been 2-dimensional calculus, right? We can find the equation of a tangent line to a 2-dimensional curve. In 21b, we can find the area under a 2-dimensional curve. But the real world is 3 dimensions, right? So we're limited if we only understand single variable calculus. So yeah, and this continues in 21c and all of 21d as well. But we'll see some of the same ideas are still carry over. Right now, the purpose of this section is to just get familiar, since we don't often talk about graphs in 3D, just getting familiar with what graphs would look like and how to plot something in 3D. Okay, so I want to plot the point 2, 4, 6, x, y, and z. One big difference you'll notice is that we're used to x going horizontally and y going vertically, but what we have is x is now coming out of the paper and into the paper, y is going horizontally, and z is going up and down, okay? So to plot the point 2, 4, 6, if that was the origin, you would go 2 units in the positive x direction, turn and go 4 units in the y direction, and then up 6 units. So you'd be at this point. Now it really is just this point. You can tell I just added some extra auxiliary lines to make it look like a box so that it gave it more of a 3-dimensional feeling. Some terminology. In 2D, we're used to the 4 quadrants, right? Starting in quadrant 1, 2, 3, and 4. In 3D, we actually talk about 8 octants. And you can kind of visualize that as, if you think of this box right here as a room in a building, a multi-story building, how many rooms on the same floor would share the origin? There would be 4, right? And if you went downstairs below, there would be 4 rooms that would look up and see the origin. So altogether, there would be 8 rooms. So that's why we call them octants. Now, the numbers of the octants are not important. Like, no one will ever ask you, where is octant 5 or octant 7 or something like that. The most important one to know is the first octant, which, just like the first quadrant, is where x, y, and z are all positive. So this point we plotted here is in the first octant. Okay, we should talk about the 3 coordinate planes. And the 3 coordinate planes are the xy plane, the yz plane, and the xz plane. A plane is a flat surface, okay? So the xy plane, we call it that, but it's all of the points where z equals 0. Back on my picture here, it's like the floor of this box, right? Every point on that floor has a z value of 0 because we haven't gone up or down. Okay, and you can think of it as being spanned by the xy axes, so we call that the xy plane. The yz plane is when x is 0, so that's a vertical wall. And then the xz plane is also a vertical wall coming in and out of the paper, also called y equals 0. Now there's other planes too. In fact, I selected, if you think about the top of this box, that's a flat surface as well. And what's true is every coordinate has a z value of 6, no matter where I am. So this would be a horizontal plane, z equals 6. Similarly, this side of the box, every point on the side of the box has a y value of 4, so we call that y equals 4. And then the front of the box would be x equals 2. That's also a vertical plane. So you have to get used to, in 3D, we're used to, for example, of seeing y equals 4 and thinking of a line. But now when you see y equals 4 or x equals 2 or z equals 6, you should be thinking that's a plane. That's a flat surface. Okay, there's also spheres. That's a shape we're familiar with, but it's 3-dimensional as well. Here I have drawn a sphere centered at the origin with a radius of 3. And it's really just an extension of the circle formula. It would be x squared plus y squared, but now you would have a z squared equals 9, the radius squared. And in general, of course, your sphere doesn't have to be centered at the origin. If it would had a center of h, k, and m, then your sphere would look like that. All right. So what we're going to practice here is, what is a geometric description for the set of points that satisfy the given conditions? In other words, what are all the points that satisfy both of these equations? Well, we just talked about x equals 2 is a plane, right? Going through the x-axis at 2. Y equals 4 is also a plane. So points that satisfy both of those can be thought of as the intersection of those two planes, which would be in a straight line, a vertical line L. Okay, the intersection of two planes is a line. X squared plus y squared equals 4 has the form of a circle with a radius of 2 on the xy axes. If we also are told that z equals 0, then that circle is drawn on the xy plane, right, where z value of 0 right here. So, you know, it doesn't look like a perfect circle where there's that three-dimensional perspective, because we have the axes kind of at an angle so we can see it, but it would be a circle. If it didn't have, by the way, if it didn't have this restriction where z equals 0 and we just had the equation of that, what you can imagine then is this, the z wouldn't matter. So if you stretch this circle out in all directions, it would be a cylinder. Okay. Here's another one that has the form of a circle in the xz plane with a radius of 2, and also y equals 0. So we're right here on the xz plane. That's going to look a little strange because that circle's coming in and out of the paper. Okay, but it has a radius of 2. It's also a circle. Okay, here's another one. Z equals y squared. That definitely has the form of a parabola that's opening upward, where you're treating y kind of like x and z kind of like y. And then if x equals 1, then that parabola, you can imagine going to the plane x equals 1, and that parabola is contained in the plane x equals 1. We can use inequalities. If we have x is between 0 and 1, y is between 0 and 1, and z is between 0 and 1, then all of the points that satisfy all of those would actually be a solid cube, where each side is equal to 1. X squared plus y squared plus z squared is less than or equal to 1. That would be all of the points not only on the outside of a sphere of radius 1, but inside too, because it's everything less than or equal to 1. Now, if we also throw in z has to be greater than or equal to 0, that means it's not going to be the bottom half of the sphere, because that would have z values of 0, less than 0. So this would be a solid top half of a sphere with a radius of 1 centered at the origin. A little more practice on this. Describe the set of points with an equation or pair of equations. So what would be the plane that passes through 3, -1, 2 that is parallel to the xy plane? Now that we know the xy plane is like z equals 0, this would have to be a horizontal plane. And remember, a horizontal plane is just going to be z equals a number. So in this case, that should actually be z equals 2. Okay, change that to z equals 2. My point was 3, -1, 2. And if it was parallel to the YZ plane, then that would have to be a vertical plane x equals 3. That's out away, parallel to the YZ plane. And the line through that same point, 3, -1, 2, parallel to the y-axis, so going in the same direction as the y-axis, would be the intersection of those two planes that we just wrote, which would be z equals 2, x equals 3. And if you put them together, then that we would understand that that's really just a line. Okay, there's a lot more to talk about with three-dimensional graphs. But for now, this will get us by as we move into vectors, and we will talk more about graphing in 3 dimensions in the near future.